Good afternoon, everybody. Right, so today I'm going to be going through the International A-Level, the IAL Chemistry Paper 4.
Good afternoon, everybody.
Oh, sorry, just
right.
pause my YouTube video.
Today I'm going to be going through the International A-Level.
There we go, let's go to that. Popped out the chat. I'm good. Now I know that I haven't told any of you guys or any of my students that I'm going through this paper this time, so we'll see if any of them join me. But as I said, I'm going through the paper 4. Now, yesterday I did the paper 4 from January 2020. Now, I decided to now do the paper 4 again, just because it'd be quite nice to be able to look at the continuity between these two papers. And it means it's fresh in my mind. I've kind of run through those kind of sets of calculations already, and we'll be able to see if there's any kind of similarities between the two of them and whether or not we can pick up any trends. I think that's quite useful. Okay, so I'm going to share my screen. Let's crack on. Now, this webinar will take about 2 hours to complete. That was how long the last one took me. I assume it'll be something similar. It'll be interesting to compare the total length of time. I'll switch my camera over to my clip cam. There we go. Hello. Right, let's go to that. Okay, so I'll change my tablet into tablet mode. There we go, go to the keyboard. Got my little fan set up, mostly good to go. Got my calculator on standby. I've also got the data booklet that's going. This is the new data booklet. Can I just say, thank goodness they got rid of the old one. The old one was about 50 pages long. It was epic. I actually gave lessons lessons 2 years ago, just based on using the booklet, because it required a little bit of translation. So luckily, this one is much, much shorter, about 8 pages, I believe. So this is the book. See where it starts. So this is where it starts. Physical constants that were provided, page 1. Then drops into your IR vibrations and bond stretching, whatnot. And then we drop into our NMR, followed by, for proton and C13, all the chemical shifts. We've also got electronegativity values, which is really nice. And we've got indicators and electrode potentials. Now, the electrode potentials, of course, the periodic table. The electrode potentials is for paper 5 and 6. And, of course, we use the NMR for paper 4 and the indicators, of course, for paper 4. So it's nice to know that that's there. Okay, so June 2020, paper 4. Starts off with multiple choice. Okay, so section A. So bromine oxidizes methanoic acid, carbon dioxide. So a powerful oxidizing agent there in terms of bromine. We know that methanoic acid is at the tail end of oxidization of primary alcohols. We have primary alcohols oxidized to aldehydes, oxidized to carboxylic acids, and it stops. It just shows you how powerful an oxidizing agent bromine is there. Which of the following methods would not be suitable for measuring the progress? So the first thing is colorimetry is all about color. And this would be totally appropriate because we've got bromine in here, and bromine, of course, is aqueous, so it's starting orange. And we're forming colorless solutions. So that would be totally appropriate. Measuring electrical conductivity, yes, because we're producing H+ in this particular reaction. And what we know is that if you've got the presence of ions, it means that your conductivity would increase. So that one's a very reasonable one. Quenching and titrating with acid. Now, that one, looking at the equation, is not appropriate. The reason being is, if you're quenching, the word quenching means to stop. Now, in this case, what they'd probably be doing is looking to remove the H+ from the reaction, and they'd be doing that with a base. Now, that wouldn't be particularly appropriate because it would also affect the amount of carboxylic acid that's left over at the end. So that one would not be appropriate. The next one is measuring the volume of gas, totally appropriate, because the gas being the product at the end, we could just be collecting gas as this reaction progressed. So very possible. So quenching and titrating, by the way, if you were going to do the quenching and titrating, you'd be titrating with a base, if anything. So not particularly useful. Okay, question number 2, a nice bit of rates. So this is just usual. We'll just be given a table of data on concentrations, and we're looking for their orders. So in reactions 1 to 2, Y has been kept the same, Z has been doubled. So what now has been the impact on the rate? So what I'm going to do is now notice the 10 to the minus 3s and the 10. So it has had an effect. What we need to do is divide the bigger by the smaller to see what multiplier it's gone through. So I'm going to multiply calculator 1, 3.2 exponential minus 2 divided by 8 exponential minus 3. And that gives me a multiplier of 4. Now what you can realize is that in order for that to have happened, then Z must have been second order, which means it's either this guy or this guy for Z. The next one is in reactions, I'll just remove that. In reactions 2 and 3, Y has been halved and Z has been kept the same. And in this case, the initial rate has done absolutely nothing, which means Y must therefore be 0 order. Nice and straightforward bit of stepping there. Very straightforward, very easy. Okay, so we've got a graph, and this is a half-life graph. We've got time at the bottom and concentration. So as the time progresses, we can see that it's decreasing. Chances are it's going to be first order. If it was 0 order, it would be a straight line in half-lives. We saw this in the previous paper yesterday. We saw these graphs appear. If it was steeper like this, then it would be second order. So this looks like a first order half-life graph. And it says determine the half-life of this reaction. So I'm going to look at the initial concentration at 20 and then say I'm going to halve the concentration, which is the whole point of half-lives. Yep, the half-life is the amount of time it takes for the concentration of that particular reactant to halve. So I've halved the concentration down to 10. Draw the line across to hit that particular part of the line and then pull it down, which is there. It'd be nice if I actually had a straight line there. There we go. Okay, so I can now zoom in, check the time. So we've got 400 to 600, so this is going to be 500. What that means is this is going up by 20s, 420, 440, 460. Seems very reasonable to me. Okay, moving on. Okay, so propanone reacts with iodine in acidic solution. Okay, so this is another rates. By the way, this is actually technically part of rates and is part of an iodine clock process. And you can do this reaction and actually measure the rates directly based on the amount of iodine that's left in the process. You take samples, you quench it to get rid of the catalyst, which is H+. That stops the reaction, and then you can titrate to find the concentration of iodine. And when you're doing the titration, what you do is you always add starch in there to provide the blue, and then you can titrate with thiosulfate to find out its concentration. It's a very common reaction at A2, especially in Edexcel IAL. So which of the following is true? So they've given us the rate equation, and it says which of the following statements is true? The units of the rate constant are dm3 moles to the minus 1, s to the minus 1. Of the rate constant, I'll have to figure it out. So we know that rates is moles per dm cubed per second. We know that that's always the same. And that these guys are in square brackets. So these are moles per dm cubed to the power of 1 and moles per dm cubed to the power of 1. What that means is if I reorganize this, I bring the moles, and that's 2 of them. The moles per dm cubed of one of them is going to cancel out, but the other one won't. So that's going to remain on the bottom, and then we've got to flip the sign. So it becomes moles to the minus 1, dm to the plus 3, s to the minus 1. That is correct. So I'm going to go for A on this one. I will just check the rest of them since I'm here. The reaction is first order overall. No, that's not correct. The overall order is the sum of the orders of each of the reactants in the rate equation. In this case, the overall order would actually be second. The units for the rate are moles, are dm3 moles to the minus 1. So that's not correct because those are reversed. So that's not correct either. Doubling the concentration of propanone and of iodine quadruples the rate. Oh. Oh, I don't like that. Because that one suggests that one should be true as well. Because if the overall order is 2 and we doubled the concentration and of iodine quadruples the rate. Yeah, so hang on a minute. Oh, there's a problem there. We're going to multiply the propanone and of iodine, doubling the concentration of propanone and of iodine quadruples the rate. We would double the iodine as well. Oh, hang on a minute. So that's overall times 4. So that's not going to be true. It's going to multiply it by a factor of 8. So that's not correct. I had the same problem in the previous paper as well, and I ran some simple numbers. So what I did was, it's caused me the same issue. I seem to have an issue with this particular fact. So the propanone we're going to double, yeah, and that's to the power of 1. And iodine we're also going to double, yeah, which is power of 1. And if we do, and we treat K as 1 because it's a rate constant, we may as well just ignore it. And we put the rate as 10. If I then step it through the process, the 10 would be doubled by the first one to make 20 because it's first order. And then if you double it again, it would end up being 40. Oh, that suggests it's true. Oh no. Times by 2. Oh, nuts. I had the same problem with the last one. Have I made a mistake with my units on the rate constant? dm to the minus 1. Sorry, dm to the 3. And moles to the minus 1 and s to minus 1. Oh no. Which one of the following statements is true? Oh no. This is going to be the first time I get something wrong in a while, especially this early on in the paper. Doubling the concentration of propanone quadruples the rate. Well, it would. It would. I feel like I've made a mistake on my units somewhere. Moles per dm cubed, moles per dm, top one cancels, bring them up. Flip the signs. Have I done something wrong here? No, it seems correct. I've made a mistake. Right, now hang on a sec. I need to now make a decision. I'm obviously misreading something here. Doubling the concentration of propanone and of iodine quadruples the rate. I think that is definitely true. I don't like that my units have been written in a funny way, but it doesn't mean that they're wrong. If we double those and they're both first order, are they first order? Yeah, they are first order, definitely. Oh, hang on a minute. Oh, found it. Iodine's not in the rate equation. So that's not true. I'm good. Do you know what? That's a fascinating point, isn't it? Because I've just wasted a whole load of time on that question purely because of a misreading. I'm so glad I spent a little bit of extra time on it to solve that. It would have really irritated me. Iodine's not in the rate equation. That's H plus, not iodine. Oh, that's clever. So it would only double it. Lol cats. Moving on. Which of the following is not true? The reaction rate increases with temperature is raised, always. The rate constant increases with temperature is raised. Yes, that's true as well. The addition of small amounts of sodium hydroxide decreases the rate of the reaction. Yes, because you're removing the catalyst. The rate is unchanged when the hydrogen ion concentration, that's not true. That's the answer there. The reason being is if you add sodium hydroxide, it will remove the catalyst from the reaction, the rate will slow down. But H plus is also in the rate equation, which means if I change the hydrogen ion concentration, then I'm going to change the rate of reaction. So D is definitely incorrect. Moving on. Okay, the equation shows the hydrolysis of a bromoalkane. And they've given us the rate equation. What this is telling us is that the only person in the rate equation is the RBR, and OH minus isn't. So what that tells me is that the reaction is a nucleophilic substitution reaction, but it's going through what's called an SN1 process. Yeah. Now the SN1 is that the number of species in the rate determining step is only one of the two reactants, hence the RBR bit. Now, what that means is that the halo, the bromoalkane, is going to be tertiary, because we know that tertiaries preferentially go through SN1. Bromomethane is primary, 2-bromopropane is secondary, 1-bromo-2-methylpropane is primary, 2-bromo-2-methylpropane is tertiary. So that one's going to be much more likely to be RBR. The equation for an exothermic reaction is shown, okay? Which is true. Delta H is positive. No, it's not. That's garbage. Because an exothermic reaction has minus delta H as its symbol. The delta S surroundings is positive. So delta S surroundings, delta S equals minus delta H over T. Now that's quite clever, that, because the delta H itself is negative. So it's going to do negative times a negative, which gives me a positive. So the delta H surroundings will indeed be positive. The entropy of the system is negative. So we're going to lose disorder. It's going to become more ordered. Well, we've gone from a solid aqueous to aqueous and gas. That's incorrect. That's going to have a positive entropy of the system value, and therefore the enthalpy total is negative. It's very unlikely because the exothermic one will end up with a really large surroundings, and the entropy decrease is going to be small because we measure that in joules, whereas enthalpy is measured in kilojoules. So the delta H has a much larger impact on delta S totals. That's probably incorrect as well. So I'm happy to go with my answer of B. Next, the equation for the equilibrium decomposition of hydrogen iodine into hydrogen iodine can be written in two ways. Okay, they've written the standard equation and they've written the equation divided by 2. So, and then the equilibrium constant Kc. So we learn about this whole trick. Can I just point out, this is purely maths games. And I teach these important games because they're common fact, it's common appearances in chemistry papers. Now in this case, if we called this one Kc original and this Kc new, in order to get to this new one, we've halved the equation. Yeah, well, in order to do this, the game with this, because their powers are halved, we have to root it. So what that means is that to move from Kc original to Kc dash, we'd have to root it, but that doesn't mean that they're the same values. What is the expression linking the two equations together? So there's Kc original and Kc dash squared are the same value. That is correct. Kc and Kc dash are not the same because in order to go from this, let's call this x, well, this is going to be root x, which is not going to be the same thing. Kc equals 2 Kc dots. No, well, that's just complete rubbish. And then Kc has actually told us how to translate one to another. And the key thing there is the equal sign. Yeah, they don't, the only time, if we want Kc dash to equal Kc, then what we have to do is we have to take Kc dash and square it. That would make it the same as. So A is the right answer. A buffer solution contains ethanoic acid with a concentration of this and sodium ethanoate concentration of this. What's the pH of the buffer? Now, whenever I teach buffers, I always tend to mention the fact that it's usually going to be within the 4.5 range. So I'm going to bet it's going to be one of these. I tend to say the last one I calculated, by the way, in the paper 4 from last year was from January was 4.89. I had a rounding error on this, which still bugs me. But we can run this anyway. So what we're going to do is we're going to write our buffer equation, which of course is the roadmap. I'm just going to treat this as HA since this is this is A minus salt all over HA. Now I can treat this as HA because it's a multiple choice and there's no marks for working out, which means I don't need the real one. So the buffer solution contains ethanoic acid at 0.1 and sodium ethanoate, the salt, at 0.05. Reorganize that to give me H+, so bring the bottom up 0.1 and then divide that one by 0.05. That will give me H+, so calculator on 0.1 multiplied by 1.7 exponential, mainly 1.7 exponential minus 5 divided by 0.05 gives me 3.4 minus log answer, and I get a pH of 4.76. That's 4.68, which is 4.47. Told you it would be the middle value, 4.5. Always a good shout. If you ever get stuck on a buffer and you can't work it out and it's multiple choice, go for 4.5. Unless it's a basic buffer and then choose about, I don't know, something like that. I don't really do, basic buffers are much less common in A-level. Which of the graphs, okay, so they're given us pH graphs. We had one of these last time, I believe. And this time it says, question number 1, which graph has ethanoic acid as one of the reactants? Well, ethanoic acid is a weak acid. So we're going to have one of these graphs is going to end or start at about pH 3, which is this guy. So that's going to be graph number 4. This is nice and easy. I'm recovering some of that lost time from misreading that iodine question. Which graph shows a solution which has an acidic pH at the end point? Can I just point out, end point means the end of a titration, and it needs to be acidic. So it depends which indicator they use. That's a garbage question. Because the first one would indeed have an acidic ending in the end point because the indicator you're going to use is probably methyl orange, but you could, of course, use phenolphthalein, in which case the end point is above, so that's garbage. What they're doing is they're saying which one's going to be going to have it shouldn't be end point, it should be equivalence point. I feel like there's a disservice going on here. Because again, same thing, depends on the indicator you use, but this one, the vertical region is always in the acidic. So we must I guess what they're saying here is that because you could have a different indicator that these wouldn't work, but this one you have to have an endpoint in the acidic region, and you're going to be focusing on methyl orange there. So that's going to be graph number 3. Which indicator is suitable for graph number 3? Okay, so graph number 3, and they want me to use the booklet. Okay, so I need my indicators. Okay. Now the equivalence point of this is low. So we've got to be, we've got a very narrow vertical region here. So we need an indicator that changes anywhere between 4 and 6. So let's have a look at our data point. So pH range 4 to 6. Bromophenol blue is just about inside it, but the problem is that won't work because it's going to go early. So don't want that one. 4.2, 6.3, not great. Litmus. That litmus would be usable because it's going to change at 5. Yeah, and that's inside the vertical region. 6 is pushing a boundary. 6.8. I'm going to go for litmus. I'm going to go for litmus. Oh, it's not even on the list. LOL! Oh, that's pretty funny. Oh, that's really entertaining. Okay, let's have a look at, oh, stop it. Let's have a look at my options compared to the ones they offer me. Oh, that's really funny. That's proper just cracked me up, that has. Right, hang on a minute. Let me have a look at these. Stop it. Okay, and then move that over a bit. I'm losing time here, but it doesn't matter. So, bromo crescel green. Would that be appropriate? Gonna go early, 3.8. Bromothymol blue, 6 to 7. That would probably be appropriate. Yeah, this one's gonna go early. Bromothymol blue could be. Phenol red, no, past it. Thymol blue, no, way too early. So the closest one I get to is bromothymol blue. So there's my answer. It's an interesting one, that. Clever. It took away some of my choices. Oh, mechanisms. Nice. Draw which diagram shows the first step in the mechanism of nucleophilic addition of hydrogen cyanide with propanone in the presence of potassium cyanide. So all of them are wrong. Yeah. Because if you do any mechanism, you have to show the charge on the corresponding person. So Edexcel's, this diagram's already garbage and it irritates me, but whatever. That, though, is a correct diagram. We're starting at the lone pair, ending that. Your deltas are correct, bond breaking. This is good. So I'm going to assume that A is correct, and the outcome, by the way, is also correct. So that arrow there, garbage. Delta's the wrong way round, garbage. Arrow, wrong way round, garbage. Okay, moving on. When propanone reacts with iodine in the presence of sodium hydroxide, so this is the iodoform test. I'm just going to quickly check. I've got nobody on channel yet. Got nobody on channel. My internet doesn't seem to be great, which is not ideal. I'm hoping that it's okay. It hasn't told me that it's terrible yet, but I wouldn't mind having someone on channel just to tell me if it's okay. In fact, what I can do is, if I just taking a bit of a breather here, guys. I just want to check that the quality is okay and that this is all functioning all right. It's okay. In fact, what I can do is, if I just okay, it seems to be all right here, guys. If I just increase the quality to as best as possible. It's okay and that this is all functioning all right. Yeah, it seems to be okay. In fact, what I can do is, I'll get rid of that now. Let's get rid of that. Okay, it seems to be okay. Let's keep going. As I said, I just keep seeing the internet things gone way down, which is really irritating. I don't know whether or not that's my internet. Well, it definitely is my internet, isn't it? So I want to try and, which one am I on? 5G. I don't know what's the cause of that. No, it might be awkward if it got cut off. It's saying it's ideal. Connection is unstable. Connection is fairly good. Okay, let's continue. Okay, so when propanone reacts with iodine in the presence of sodium hydroxide, it's what I'm tempted to do. I'm tempted to message one of my students and tell them to come online, because that would be really handy. Well, maybe I won't. Okay. So this is the iodoform test. When propanone reacts with iodine, the precipitate formed is the following. So that's just that one. That's just kind of something that you just have to learn in the iodoform test. Which of the following? Can I just point out, by the way, iodoform plays quite an important role in synthesis. This is commonly not talked about by many teachers, and including myself at times. The iodoform test can be used to shorten a carbon chain. If you run the iodoform, you'll cut off the last carbon next to the acetyl bond O, and you'll leave the remaining organic compound as a carboxylic acid, or actually a carboxylate salt, technically, but it does shorten the chain, so something to consider. Which of the following could not be formed when methylamine is added to ethanol chloride? So ethanol chloride is, we'll draw that one out. Ethanol chloride with methylamine. So what's going to happen is we're going to form HCl. You always form HCl on the back of this. So that one can, yep. Methyl ammonium chloride, yes, that can happen because if you've got the amine in excess, it'll react with the HCl and turn into the ammonium chloride salt. So yes, that can be. That's ethanamide. No, that can't be made. So there's my answer. The reason being is there's no actual ammonia here. Yeah, it's just it's an amine, which means what you'll do is you'll always tack on the nitrogen and a carbon, which is what that one is there. So it seems reasonable. Which of these esters is the percentage by mass of 54%? Seems to have gone with the single now, which is good. 54%, that's horrible. That's just going to take me time. I've got to work out the MRs of each of them. So let's do the first one. The great thing is, though, with carbon, this is 2, so it's relatively easy. That's going to be 24 over, and the total, so 1 plus 12 plus 16 plus 16 plus 12 plus 3 equals 24 over 60 times 100. It's not 54%. Don't even need to run it. It's less than 50. Next one. So this now is 3 carbons. So this is now 36. I'll step this out. 36 over what's now the total of that guy. The reason why I'm 36 is because I've got 3 carbons, by the way. So I can take 36 and add on the other people. Add on the hydrogens there at 3, plus the 2 oxygens at 32, plus 3 at the end. Oh, calculator error. Plus 3, plus 32, plus 32, plus 3, and 36. Over 74. So 36 times 100, 36 over 74 times 100 gives me 48%. So that's not enough either. This is just taking me time. So this has now got 4 carbons in it. So 12 times 4 is 48. So 48 over the total. Now just add on all the rest of it. 48 plus 3 plus 32 plus 2 plus 3. And I get 88. Okay, so 88. So 48 over answer, 54.5%, which is C, and I'm done. An organic compound that reacts with both lithium tetrahydroaluminate, so this is a reducing agent, yeah, and magnesium. Magnesium is usually like, I don't know, it's a test for, well, you can use it for a test for an acid, I guess, but it certainly wouldn't react with an aldehyde. So the aluminate would, because it would reduce that. So the LiAlH4 would turn that back into a primary alcohol. So that one would work, but the magnesium, no. The carboxylic acid would be reduced to the aldehyde and then down to the primary alcohol. So that one will with the lithium tetrahydride, and it will also with the magnesium because it'll form hydrogen gas. So there's my answer. The ketone would be reduced to a secondary alcohol, but it wouldn't react with the magnesium metal. The tertiary alcohol can't be reduced any further, so it wouldn't react with that, and it probably would react with the metal, but it would be very, very slow. Very, 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 very slow. To test for an alcohol, the generic test is sodium metal, not magnesium metal. But anyway, moving on. Okay, did I fill it in? Yeah. So the following method can be used to distinguish between pairs of organic compounds with no further tests. Okay, given us a list of tests, A, B, C, D. Which test would be used to distinguish between 2-methylpropan-2-ol, which is a tertiary alcohol, and butanone? Okay, so Fahling's and Benedict's reagent will test for the well, no, it won't, because it's a ketone. It won't oxidize it, so that one won't work with A. Would it work with the alcohol? No, it's a mild oxidizing agent and it's tertiary, so it will resist it. So that one won't work either. Warm with acidified potassium dichromate. You can't oxidize the ketone and you can't oxidize the TA, so you can't do that either. Add 2,4-DMPH to each compound. That will detect the C double bond O, so that one will work with that, but there's none in that one. So the answer is C. A few drops of each compound, drop by drop to water. Yeah, that's not really going to help. It's not going to give you a really good solid test. That's garbage. Which test would distinguish between tertiary alcohol again, but this time butan-1-ol, a primary ol. Okay, so this one's going to be the acidified potassium dichromate, the test for the alcohol, so that's going to be B. The reason being is a tertiary alcohol will resist oxidation, but the primary alcohol will go to the aldehyde and then onto the carboxylic acid. So that one will distinguish between the two. The Phalings won't, because it won't do either. Yeah, the Bradley's reagent, there's no C double bond O, no 2,4-DMPH, so no C double bond O, so that won't do it with those drops of water. They're both soluble. Although the butan-1-ol will be less soluble, it'd be difficult to tell the difference. Which test could not be used to distinguish the tertiary alcohol again, and this time, a butanal, so an aldehyde. Okay, so Tollens reagent, Phalings and Benedict's will be able to. Yes, that one will work because the Phalings will oxidize the aldehyde, but not the tertiary alcohol because it's an oxidizing agent and it's actually the test for aldehyde, so it works. Warm each with acidified potassium dichromate, that will also work because the tertiary alcohol will resist oxidation, the aldehyde will go onto the carboxylic acid, so that one will do as well. Add 2,4-DMPH. 2,4-DMPH will detect the C double bond O in the aldehyde, but not in the tertiary alcohol. So that one will work as well. Adding the drops to water, it makes sense. The tertiary alcohol will dissolve in the water and the aldehyde will dissolve a little bit. 4 carbons, So I'm going to say D, because the other ones that can, so D seems like the reasonable answer. That brings me to the end of the multiple choice at this stage. How long has that taken me? 32 minutes. I'm a little bit behind schedule there. I was on 30 minutes in the last one. I know that I had to fix the internet and I had that stupid question that foxed me, but still, 30 minutes. Okay, Born-Habers, we saw one of these in the January paper as well. So this case, what they've done is they've given me all the data, complete the Born-Haber cycles by writing the appropriate chemical formula on the horizontal lines, including state symbols and any relevant electrons. Okay, so I actually don't need the data for this at all. This is me knowing, I do, because they've just, they're not actually assigned to anybody. Okay, fine. So, right, do they give me ionization 1 and ionization 2 to be calculated. So let's do calcium metal first. So I'm going to first of all take the calcium and I'm going to turn it into a gas. This is atomization of calcium. I'm going to reduce my pen size here. And the chlorine gas, which is still a gas. Still not now finished with calcium. I'm now going to turn the calcium into a calcium 1+ ion gas, and I'm going to include its electron on the equation, and the chlorine still has done nothing. Next, we now take calcium and ionize it again to form calcium 2+ gas plus 2 electrons, and the chlorine is still not done anything, but now we're going to do that. Now we're going to split the chlorine up. We're going to take the calcium 2+, that remains there as a gas, and then we're going to add the 2 electrons on there for that one, but now we're going to split the chlorine into 2 chlorine atoms, and they're still gases. Right, now what we're going to do is we're now going to have the electron affinity for the chloride ion, which is then correct, and the last one. So that seems all very reasonable to me. Yeah, and that's 4 marks. I've just saved myself a boatload of time because I'm well practiced on Born-Habers, like that. Calculate the second ionization energy of calcium using the cycle and the values given in the table. Include a sign and units with your value. Right, so once again, they've asked me to do the second ionization energy, which is here to here. This is where I start. This is where I need to end. I'm going to have to go in the opposite direction all the way round. Yeah. And then up, and then across, and then down. And I'm done. That's my other direction. So what I can now do, and I know this is going to be a little bit awkward for you guys. I'm sorry if you can't see it. The issue I've got here is my data. What I'm actually going to do is, because I usually in the exam, you have the data, the pages next to each other in a book. Well, if you're flipping backwards and forwards, that's a nightmare. We'd hope these would be next to each other. But what I'm going to do is I'm just going to do the answer over here and then copy and paste it over, because that would save me a bit of time here. So I need to start down here. Yeah, so the first one is going against me. So I need to go, so my question mark, which is here, question mark equals, going to create the equation first. So the first one is going to be, this one was the first ion. By the way, the first thing is it's against me. Yeah, I am moving in this direction and the arrow is going there. So this is against me. So against me, brackets. Right, what value is that? That's calcium ionization number 1. Find that in the table. First ionization of calcium, plus 590.0. Close brackets. The next arrow is also against me. Against, close brackets. Right, this is now the atomization of calcium. So atomization of calcium is plus 178.2, close brackets. The next arrow is now with me. Notice that that arrow is with me. So I can now go with me, close brackets. This is the standard enthalpy of formation. So the standard enthalpy of formation, which is minus 795.8, close brackets. Next arrow, which means that translates across, which is this one here, and I'm going in this direction, so it's now against me. So I can now brackets. This is the lattice enthalpy of formation, standard lattice enthalpy, which is minus 2258, close brackets. The next arrow is also against me, so that's going to be against me, close bracket, open brackets. And this is the electron affinity for chlorine, but times 2. Yeah, that's important, times 2, because there are 2 chlorines forming chloride ions, and I'm given the electron affinity, which is there for only a singular. So that's minus 348.8 times 2. Right, I've gone through that one. I'm on to my final arrow now, which is going down with me. So I'm going to go with me, open brackets. And this is the second, nope. This is the atomization of chlorine, or actually the bond dissociation. Now, they've given me atomization, which is to form 1 atom, but I have formed 2 atoms in my equation. So once again, times 2. Times 2 of 121.7, and that's plus. Close brackets. Right, run that all through my calculator in a straight line. So, minus brackets, plus 590, close brackets, minus brackets, plus 178.2, close brackets, plus brackets, minus 795.8, close brackets, minus 2258, close brackets, minus brackets, 2 times minus 348.8, close brackets, plus brackets, 2 times plus 121.7, close brackets, equals. And I have just got the second ionization as an enormous value of 1,635 positive, which is very reasonable for removing the second electron from calcium. So I'm now going to take that whole set of working out, which I would have written down, by the way, in the space. It's going to move that down here. There we go, because that's where all my marks come from. It did say include my units, which is kilojoules per mole. And I'm done. Moving on. The theoretical energy of formation of calcium chloride, of lattice energy, is 2223. Explain why the experimental lattice energy is more exothermic than the theoretical value. Right, so this is the discrepancy against the PIM. We had something similar to this on the previous paper. So the first thing is, so the theoretical lattice energy, so the little CaCl2, the theoretical one that's calculated by the physicists is this. Yeah, that's theory. But then the one calculated from the Bourne-Haber cycle is more exothermic. So let's go that at like 300 or something. So the reason being is, so number 1 is calcium chloride, CaCl2, has partial covalent character. Partial covalent character. And this is due This is due because we had something very similar in the January paper. because calcium 2 plus has a high charge. Calcium 2 plus has a high charge density. High charge density, and is therefore very polarizing. And so very polarizing. Polarizing. And the chloride ion, so the chloride ion is distorted. Now, the last bit is to therefore say, so lattice enthalpy requires more energy to break. Energy required, energy to break lattice, yeah, which is, oh, no. So we're forming stronger bonds. They're forming, requires more energy to break. Energy released on the formation of stronger bonds. Yeah, energy to break. I can actually do the converse. Energy to break, but they want me to say why it's more exothermic. Energy released, so therefore, energy released is greater, since bonds are stronger. Since bonds are stronger. Or electrostatic attractions are stronger. It's not really bonds, electrostatic attractions. Since attractions are stronger. Made a mess of that. Sorry about that, guys. Moving on. Okay. So explain the trend in theoretical lattice energy on descending group 2. Okay, so we've got magnesium 2 plus, Mg 2 plus, and Cl minus. Then we have calcium 2 plus, Cl minus. Then we have strontium 2 plus and Cl minus. And then you have barium 2 plus and Cl minus. So the first thing to spot here is as we descend, as you descend group 2, the ions increase in size. That's going to be first mark. Now, what that then means is that, now what's interesting is the lattice energy. So it's becoming less covalent, yet they're getting weaker. This one's going to have covalent character. This one we know has covalent character. This one has less covalent character, and this one is almost purely ionic. So we can say that the amount of covalent character, in the compounds decreases. Due to anion being less distorted. So less energy is released on formation since bonds stroke attractions are weaker. Done. Okay, next. Calculate the enthalpy change of solution. Oh, I love these. Now, this question in the January paper put me in a really stupid Hess cycle picture. I'm now going to get to show you how I like to do these. So calcium chloride, you literally say calcium chloride 2 as a solid, going to calcium 2 plus aqueous, going to Cl minus aqueous, and don't forget to balance. And then you say, now you never label that arrow, now we go to gases, Ca2 plus gas, plus 2Cl minus gas, and now you go to hydration enthalpies are gaseous to aqueous, and they gave us a negative value, which means it is being formed, so it's going up. That's the cycle that I teach. I actually teach it in like a silver nitrate setting usually, or a sodium chloride setting. Yeah, I just say learn this cycle and be able to adapt it to what fits. Now we just need to apply all my numbers. So the lattice enthalpy is minus 2258. And then the hydration of calcium is minus 1650. The hydration of chloride ions is 364, but there are 2 of them. And we're after this guy. So this way equals this way. So this arrow here is against me. So I'm now going to create my equation on the back of this. I know that I've run out of space. I wouldn't have made it quite so big in my real exam. I would have been like, okay, there's no space on the next thing. I should continue to try and make all this work, and I can actually. So if I'm going this way and this way, this one's going this way, so that becomes question mark, shouldn't do that, question mark equals minus, which is against me, minus 2258, close brackets. Now I'm going around the cycle in this direction. This one's with me, so plus brackets minus 1650, close brackets. This one is also with me, so plus brackets minus 364 times 2, close brackets. And just simply run that through my calculator in a straight line. So calculator on, minus brackets minus 2258, close brackets, plus brackets minus 1650, close brackets, plus brackets minus 364 times 2, close brackets, equals, and I get an entropy of solution of minus 120 kilojoules per mole. Seems very reasonable to me. It's exothermic, calcium chloride into water, sure. This is a bit high maybe, but I think that seems reasonable if I just check through my calculation. Yeah, okay, no, I'm okay with that. 2258 seems reasonable. Okay, moving on. Okay, this question contains 6 isomers, each with the molecular formula C5H10O2. So this is the puzzles of Unit 4. They're going to be dropping us into NMR chiral centers. We had something similar to this in the multiple choice in the January paper. Isomers A, B, C, and D are structural isomers, react with aqueous sodium carbonate. Oh, all isomers A, B, C, are all structural isomers that all react with sodium carbonate to produce carbon dioxide. Okay. Which means they're all carboxylic acids. Okay. Isomer A is a straight chain compound. Give the structures of the 4. Okay, so that's pentanoic acid. Pentanoic acid, all mistakes. In the exam, I would always show the hydrogens, so I will also do that as well. There we go. I'm in an exam setting. It's nice to see the time it takes. There's pentanoic acid, straight chain. Isomer B has only 2 peaks in its high-resolution proton NMR spectrum. Branch it, branch it, branch it, both of which are singlets. Branch, 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 branch. Branch them all, baby. There we go. That makes total sense. All the ones on the outside, all of these guys here that I'm now drawing are all in the same environment. So they just give a single peak, and there's nothing on that middle carbon, which means it's a singlet. Yep. Fine, that's B. C. C contains a chiral center, but isomer D does not. Okay, so contains a chiral center. Contains a chiral center. Now put all the pieces on that you can. Yeah, put a H on there. How many carbons do I have left? 3, so I'm going to put a CH3 on that guy. That's clever, isn't it? That's the way I always do that whenever they say chiral centers. Draw a carbon and then make it different. There you go. There you go, that works. It's all a game. So that's central carbon. Then the next one said the next one doesn't. Okay, that's a bit more tricky, that. Oh, I have a question. Or at least I have some message. I'm assuming it's going to be. I'm not going to answer that. The next one does not have a chiral center, but is then not the same as that guy. That's awkward. Not a chiral center. Got to be a carboxylic acid. Oh, okay, that's clever, that. Yeah, okay, put the methyl group on the second, on that carbon there. Yeah, that works, because they have 2 of the same groups. That's neat, that. I like that one. Yeah, that works. So this carbon is not chiral. This carbon is not chiral because it's got 2 H's on it. This carbon isn't chiral because it has this group and this group, which are the same. And then the last 2 can't be either. That's really clever. I like that one. Made me think a little bit more. I like it. There we go. Moving on. Moving on, next. Okay, isomer E contains an ether functional group. Low resolution NMR, 4 peaks displayed. Okay, I'm gonna have to look back at my thingy sheet, my data sheet for the relative shifts. But, so they're telling me that A is a singlet at, oh, hang on a minute, in its including the high resolution. Okay. A is a singlet, relative area 3, fine. B is going to be a triplet. It's going to be a triplet. The reason being is the carbon next door has 2 on it. So it's going to split that peak into n+1, so 3. It has a relative area and integration of 2. And its chemical shift is going to be the same as the chemical shift for the previous group, I believe, because it's also on the ether group. So its shift should be the same, I believe, but let's just check. I'm pretty sure it's going to be the same. Pretty sure. Uh-oh, I've lost something. Oh no, I've lost something. Ah, nuts. I've lost something. Don't know where it's gone. Don't know where it's gone. That's irritating. I must have closed it by accident. Reopen, closed. Oh no. Reopen, close tabs. There we go. Oh, I must have closed it by accident. Right down to the bottom. There we go. There we go. Scroll up. I'm looking for my chemical shifts in C13, I believe. It was, nope, high-res proton. High-res proton, which is these guys. It's going to have the same one as an ether. CH ether. Oh, but is there a CC ether? No, there isn't. There isn't a CO ether, as in like a COR ether group. So it's in the same bracket. So that's okay. We can just copy that across 2.9 to 4.2. C is also going to be a triplet with the same area. That's a triplet split pair. But this one is now next door to the C double bond O in a ketone. Yeah, was it a ketone? Yeah, it's a ketone. So I just find C double bond O ketone, which is there, aldehyde. Nope, not, there it is. H on the C next door to a ketone. So that's going to be 1.6 to 2.8. 1.6 to 2.8. 1.6 to 2.8. Next, D is the same thing, but this time it's a singlet because there's nothing on the, there's no H on the ketone group. The integration is going to be 3, and it's going to have the same value. Yeah, so 1.6 to 2.8. I hope those are the right numbers. Be interesting to see on the mark scheme. State the number of peaks in carbon 13. 1, 2, 3, 4, 5. No symmetry. 5. Moving on. Isomer F. I'm loving this game, by the way. It's nice to see so many different isomers in these questions of building them. Isomer F is a neutral compound that smells like pears, so it's an ester. Yeah. It can be formed by the reaction of V and W in the presence of concentrated sulfuric acid. V and W. Who's V and W? Nobody knows. Nobody knows the trouble I've seen. Okay, from V and W in the presence of a catalyst. Compound V has an absorption at 1720. That's C double bond O. And a broad absorption. So that's going to be OH acid. Yeah. So V is the acid. Compound W can be formed directly from propanal. That would be lithium tetrahydride or aluminate, reverting it back to forming the primary alcohol. Identified by name or formula, compound isomer F. It's got the same carbons in it. Isomer F. So this has got C5H10O2. Ah, that's clever, that. C5H10O2. Oof. Okay, so isomer F is a neutral compound that smells like pears. It can be formed by the reaction of V and W in the presence. Compound V, compound W can be formed directly. They've told us propanal. So that's got to have been. So W, identify all of the people, justify your answers with the variable information. So W must have been W is propan-1-ol. Propan-1-ol, because the al will turn back, be reduced back to the primary alcohol. W propan-1-ol due to reduction of propanal to form primary alcohol. Primary alcohol. This is a long question, this. Next, therefore, there's 2 carbons left. What that means is that V must have been ethanoic acid. V is ethanoic acid. Ethanoic acid. Due to absorbance at 1720 and 350 centimeters. Next, F. So therefore, F is going to be the ester, which looks like this, which is propyl ethanoate. Propyl ethanoate is the final picture. It's nice to draw it out, to be fair. I do like that. F is propyl ethanoate. Propyl ethanoate. The reason being is esters have sweet smells. I don't know if I've got the 4th mark there. It's going to be interesting to see. Fine, moving on. State the conditions required for the reactions needed to form compound W from propanal. State the conditions required. Lithium tetrahydroaluminate in dry ether. Under reflux. I'm just going to go for that. State the role of the sulfuric acid catalyst. I'm actually also tempted to say it's a homogeneous catalyst. I'm just going to put catalyst. It'll be interesting. If I lose it on that mark, I'll accept it. State which one of the isomers A, E, and F has the highest boiling temperature and justify why. A, E, and F. So ester's pretty big. E or F. Pentanoic acid is going to have the highest hydrogen bonding, and it dimerizes. What the hell was F? Oh, F. What? F was the ester. A and E. What the heck was E? What was E? That was E. Okay. Yeah, no hydrogen bonding. So the answer is the carboxylic acid. A shows hydrogen bonding. All the rest don't. Yeah. So justify your answer. So the answer is A. Carboxylic acids show hydrogen bonding. Whereas ester and ether show dipole attractions. Dipole attractions. Nice, a bit of AS coming in here. Yeah, dipole attractions and hydrogen bonding. Hydrogen bonding is stronger. Than dipole attractions. So I have to have to write it all. Dipole attractions. It's nice to also put carboxylic acids dimerize. Carboxylic acids also dimerize, increasing boiling point. That'll do. Move it on. Be interesting to see how many of the 3 I get there. That one, I really like that one. Be very interesting to see what they want for that. Okay, good old acid base. Oh, I love acid base. Oh, see how fast we can do this, shall we? The question concerning a acidic solution. A solution of hydrochloric acid has a pH of this. Calculate the concentration of hydrogen ions and hydroxide ions in the solution. Lol, that's entertaining, because they want us to find the hydroxide ion concentration in acid. That's weird. So what they're saying is that we have got, number one, pH of 1.125. Well, the equation for Kw, the only equation that allows us to calculate both of those ions is these two. And the great thing is we've got that guy and we can find that guy. So 10 to the minus the pH will drop me out into the H plus concentration. Calculator on, shift, log, minus 1.125, go. I get a concentration of 0.0749, but it rounds up, 750 moles per dm cubed H plus. Fine. Well, now that can drop into there and I can reorganize the equation. Kw over H plus will give me OH minus ion concentration. So 1 exponential minus 14 divided by answer, and I've kept it on my calculator. So the OH minus concentration equals 1.33 times 10 to the minus 13. Jog on, amazing. Calculate the volume of water that must be added to 25 cents. So this is C1 V1 equals C2 V2. This is a dilution question. So it says calculate the volume of water which must be added to a 25 centimeter cubed solution to increase the pH from this to this. Perfect. So the original concentration of H plus ions was 0.0750. Yeah, and I now need a new concentration, which is the new pH anti-logged. So 10 to the minus 1.5 will give me the concentration of H plus. So shift log minus 1.5, which now gives me 0.0316 times by the new total volume. Reorganize the equation, and I will get a total volume too. So 0.0750 times by 25 divided by 0.0316, and I get a new total volume of V2 of 59.3 centimeters cubed. Now it asks you for how much must be added, which means I need to do 25, taken away from 59.3, 59.3 minus 25, 59.3 minus 25, and I can answer 34.3 centimeters cubed of water. Moving on, like it. Next, phosphoric 5 acid H3PO4 is a weak acid which dissolves in water, giving the following equilibrium. Find the acid-base pairs, identify the acid bases, and then link them to the conjugates. So, okay, so this one's acting as the acid, this one's acting as the base, then this one is acting as the look for the connection. Yeah, this is the conjugate base. Yeah, and this is the conjugate acid. Done. Nice. Cool. Explain why very little dissociation of H2PO4 minus occurs in solution of the phosphoric acid. Okay, so equation 1 is the phosphoric acid. Oh, hi, Winkit. Winkit, is the video okay? I've been having internet issues. Let me know whether or not the video's been okay. That would be grand. I'll be doing this paper. I'll be doing this tomorrow. Finished the paper 6 today. Well done, Winkit. I know I decided I did the paper 4 yesterday. I figured I'd start with the paper 4 today just to see some continuity. So this is equilibrium. So in equation 1, the dissociation of phosphoric acid, yeah, goes to form this, and then the next one. So this is Ka2. This would be technically Ka1, and this would be the second Ka. This is Ka2. It's the second one of it. And it says, explain why there's very little dissociation. So the reason being is that in the first dissociation, the first dissociation produces H2PO4 minus. Now, it also creates H+. Now that H+ would push the second equilibrium back. H2PO4 forms. Explain why very little dissociation of the ions occurs in solution of phosphoric. First dissociation produces this. Well, once it produces that, you'd expect it to go on to the next one. But it also makes H3O+, which would push the second equilibrium back. The first dissociation produces that and H3O+. The H3O+, pushes second equilibrium. Pushes second equilibrium. Second equilibrium from right to left. Also, the energy required to lose H+ from an already negative ion, is very high. Trying to split, very few particles will have EA. So, Ben, hello. Negative ion removing of H+ ion from a negative ion, very hard. Yes, correct, Winkit. I was just saying the same thing. I'm hoping I've got both marks there. I'm not entirely sure if I do. Annoyingly, I've seen this question before. It was on your mock paper. It's going to be entertaining to see the mark scheme again. Using equation 1, write an expression for the acid dissociation for Ka for phosphoric acid. Ka equals H+, H2PO4 minus, all over H3PO4. First equation. A 0.5 molar solution of phosphate has a pH of this. Calculate its Ka, stating its units. Okay, assume that no further dissociation occurs. Fair enough. Ka equals, we've got it up there. Right, what we're looking for is it's given us the concentration of this guy, and it's given us the pH. Yeah, and we want to find Ka. But the great thing is we can make an assumption. This is pure weak acid. Yeah, so Ka will equal H+ squared over the acid. The reason being is because this is a pure weak acid, the concentration of the anion and the cation must be the same, because if you lose the H+, you form the A-, so it's going to be in equal quantities. So this is called the false expression. Now, the great thing is I've got everything I need. I just need to insert everybody. So I've got to convert the pH into H+. So minus 10 to the minus 1.2 will give me the pH. No, minus that will give me the H+ concentration. So shift log minus 1.2 equals. So that's 0.0631. And then I've got the original concentration of the acid. I've got to remember to square that number. So H+ squared equals square my answer. Oh, no, that's made of mass. 10 to the shift log minus 1.2 gives me that. Square answer equals, I get 3.98 times 10 to the minus 3. Right, that now can be divided by the concentration of the acid, which is that, divided by 0.5. Gives me an answer of a Ka value of 7.96 times 10 to the minus 3. That's quite a strong acid, that. It's about 100 times more acidic than vinegar. Fine. I'm tempted to run that back through and just to see if I get the right pH. I can guarantee myself to know if that's right. Oh, don't forget my units. Moles per dm cubed, moles per dm, the bottom one cancels. It's just moles per dm cubed. Tempted to run that through there. Because if I just did really quickly, if I just did, I want to know the pH of this acid. If I go bring that up there, so 0.5 multiplied by 7.96 exponential minus 3 root answer minus log answer when I get pH of 1.2. Good. Nice. Move on. Phosphate buffer solutions contain hydrogen phosphate and dihydrogen phosphate ions. Are commonly used in biological research. Explain, using relevant ionic equations, how a solution containing these ions can act as a buffer when small amounts of alkali. We did this in the last paper. Isn't that lovely? So we've got a large residue. Let's do the original one. So the buffer is H2PO4 minus in equilibrium with HPO4 2 minus and H plus. And what we say is we have, remember the mark scheme for the previous paper, we have a large reservoir of H2PO4 minus and HPO4 2 minus, 1 mark. Right, what we then say is that adding alkali adds OH minus ions to solution. Right, those OH minus ions will react with the acid. Yeah, and the acid in this case is him. It's going to react with the acid H2PO4 minus, and it will form HPO4 2 minus plus water. Made that mistake last time. I didn't balance it. I made a mistake. We can just get rid of that. Yeah, don't need that in the equation. It's just nice to understand this. Add alkali to solution. It reacts with the acid. OH minus removed. And ratio of H2PO4 minus and HPO4 2 minus are almost the same. Done. Moving on. I've seen it in mark schemes so often. Large reservoir, usually mark number 1, right? Yes, large reservoir with both. Yes, well done, Winkit. Moving on to section C, onto the final section. How are we doing for time? My internet seems to be okay. Yeah, it seems to be all right. And we're at 1 hour 11. On into the last section, doing okay. Okay, ammonia, Born-Haber process, yada, yada, yada. Calculate the entropy of the system. Okay, so delta S system equals sum of delta S super products minus sum of delta S reactants. Right, so divide it in 2. I need products first. 2 ammonias, it's there. So I'm going to go 192.3 times by 2. That gives me the products. Yeah, I'm going to then minus brackets. I'm going to do a bracket here. I've got 1 nitrogen at 191.6 plus bracket 3 times 130.6. Close brackets. Lol. Right, there's my reactants. Let's run it through the calculator. Open brackets. 192.3 times 2. Close brackets. Minus open brackets. 191.6 plus brackets. 3 times 130.6. Close brackets. Equals. And I get minus 198.8. Right. That makes total sense. And don't forget my units. Joules per Kelvin per mole. Yeah. Yeah. Okay. Explain using ideas about disorder whether or not the sign is expected. Totally expected. This is saying losing disorder. Well, through 4 moles of gas on that side, 2 on that, massive drop in disorder. So explain it whether or not the sign is expected. Yes, expected sign. Expected sign at 1 mark. Now I just need to explain why. 4 moles of gas on left, but 2 moles of gas on right. therefore decrease in disorder. In disorder. I like it. Go. Moving on. At 700 Kelvin, the enthalpy change for the reaction is this. Calculate the surroundings. Delta S Sir equals minus delta H over T. Insert my numbers. So therefore, minus brackets minus 110.2 all over a temperature of 700 Kelvin. They've not made us do any conversion tricks in this so far. Minus brackets minus 110.2, close brackets, divided by 700. All very easy so far. Gives me, now this is now in kilojoules per mole, 0.157 kilojoules per mole. I'm going to convert that to joules, times it by 1,000, because I can see where this is going. 157.4 joules per mole. I'm happy to take. Per Kelvin. Per Kelvin. Give the units in your answer. It's got to be per Kelvin. Yeah, because the temperature's on the bottom. Joules, yeah, you get the point. Yeah, so that's per Kelvin as well. There we go. At 700 Kelvin, the total entropy change is this. Calculate entropy of the system at 700. I thought we'd just done that. No, we calculated it at 298. Of course we did, standard values. Right, so, okay, so the S total is equal to S system plus S surroundings. Well, we've just worked out the S surroundings. Notice that the total is being quoted in joules. Yeah, so we're after, we've been given the total, minus 78.7 joules per Kelvin per mole. We've not got the system, but we have got the surroundings. Reorganize. Minus 78.7 minus brackets plus 174. Here we go. Because that's always a plus, isn't it? So let's have a look at it. Right, running through my calculator. And I'm in joules, which is good. Yeah, it's minus 78.7 minus brackets plus 157.4, close brackets. So I get a total of minus 236.1. Okay, so the system, very negative. So it has dropped a little bit, but look at that. Like it's dropped by 40 joules per mole at an increase of 700. I've got to include my units. Joules per Kelvin per mole. Next, explain one advantage and one. They're almost identical on the previous paper. 6 marks. Oh, it's a lot of writing. How are we doing for time and how are we doing for questions? Okay, we're nearing the end of the paper, so I've just got to suck it up. Explain one advantage and one disadvantage of using a temperature higher than 700 in the Haber process. Right. So bullet point number 1. So disadvantage, let's do one advantage. Yeah. Advantage is a higher rate. Yeah, is a higher rate of reaction. Okay, there's my advantage. Disadvantage is a lower yield. Yield of ammonia. Now what they want me to do is they want me to explain this, consider the effect of the increase in temperature on the rate of reaction, yeah, and on the values of the system, total, and on the equilibrium constant. Okay, so first of all, let's just now clarify equilibrium constant. The only thing affecting equilibrium constant is temperature. So this one does matter. So I'm now going to say the equilibrium constant, making a mess. Equilibrium constant will be reduced, due to equilibrium equilibrium shifting from right to left. Right to left. So just to tell you how I'm doing this, folks, in the equation here, that's the Haber process. And it's told us to work out each of these things in turn. But one of the things that it's told us halfway through this question is that they told us the enthalpy change is negative. So this is exothermic in the forward direction. Just to show you where this is coming from. They're telling us that this equation, this is, by the way, I wouldn't write this down in my exam because it's a waste of time really at this point. But it's just nice for me to remind you of how I'm doing this. This is actually coming out of equilibrium at AS, minus 110.2. So it's telling us that the forward reaction is exothermic. So if you raise the temperature, you will favor so if you raise the temperature, would you add the phrase making industrially viable? I saw that in a mark scheme and why the perform the reaction at the higher temperatures. Don't know. I'll come to that in a minute, Winkit. Industrially viable. Funnily enough, 700 Kelvin is pretty much exactly what they use. They use 450. So 450 plus 273. They use 723. So interesting that they're doing that. I'm going to say it's going to be the correct compromise, Winkit. Rather than saying industrially viable, I'm just going to say it's the correct compromise. One advantage of disadvantage using this so I'm coming to that. But the equilibrium constant will be reduced. We know that the equilibrium constant is a numerical value that represents equilibrium. If you have more product, Kc and Kp are larger. Well, in this case, we're shifting from right to left because an increase in temperature will favor the endothermic process, shifting it from right to left. So we're going to decrease the products. So the equilibrium constant will be reduced. The next thing, now I need to talk about the entropy of surroundings. So now I say the delta S surroundings. Now what's actually happened to it? We actually calculated it. The delta S, oh no, we haven't. The delta S of the surroundings. What's going to happen here? We've raised the temperature. Okay, which means the enthalpy change hasn't really changed. And temperature, we're dividing it by a larger number. It's going to be smaller. The enthalpy delta S surroundings will be less what? I said last time in the paper, I made a mistake. I said smaller. I'm now just going to say that it's going to be less positive. That was the change. Delta S will be less positive. Less positive since T larger, since temperature is larger, is higher. Okay, now what effect does this have on delta S total? Therefore, delta S system will be less positive, and the delta S total will therefore be less positive. Delta S total will also be less positive. So reaction less feasible, and lower yield. Now the question, have I ticked all the boxes here? This is Winkit's bit now. I've done 5 bullet points for 6 marks here. It's nice to mention a compromise temperature temp in industry is used balancing rate and yield. Moving on. Didn't need the second page at all. It's nice. Okay. Write the expression for the equilibrium. I'm just going to check my internet. All seems to be working okay. Write the expression for the equilibrium constant Kp for the reaction. Okay, so Kp equals products. So I've got partial pressure of NH3 into the power of 2. Now, just to note here, everybody. So sometimes I just like to use a lowercase p, but sometimes you see pp, partial pressure. I just use a single p. That's what I was taught when I was doing my A levels. Partial pressure of nitrogen. But here's the next bit. You cannot at this point use square brackets. This is because square brackets means concentration. This is not concentration. This is partial pressures. Be aware, be warned. Yeah, there's my answer to this. This all seems very reasonable. A mixture of nitrogen, hydrogen, ammonia is at equilibrium at 255 atmospheres, 700 Kelvin. The partial pressure of nitrogen is this, and that of hydrogen is this. Calculate the equilibrium constant P. Okay, so partial pressures literally mean like it is what it is. It's like what it says on the box. It is the part of the total pressure. So they've given us here that there is the total pressure. And then they've given us the partials. So what we can do is, the first thing we need to do is work out. So we've got the partial pressure for nitrogen. We've got the partial pressure for hydrogen. We just need the partial pressure for ammonia. So that's the first thing we need to do. So the total pressure, 255 atmospheres, minus 25, and then minus 150 equals. So 255 minus 25, 255 minus 25, and then minus 150. And I get a total of 80. So 80 atmospheres is the partial pressure for ammonia, NH3 gas. I like it. Right, now we can just insert those into Kp. So Kp equals the ammonia 80 squared over nitrogen, which is 25 to the power of 1, times by, isn't that interesting? I've got plus, it's not, it's times. Times by brackets 150 squared. No, cubed. Right, run it through your calculator. I'm going to do this in bits and pieces. 80 squared is 6,400 over 25 multiplied by 150 cubed. That's a nightmare. 3 eek. Whoa, it's massive. 8437500. So 6,400 divided by answer. Blimey, my Kp equals 7.59 times 10 to the minus 5. And my units are atmospheres, atmosphere. So, and this one is atmosphere and atmosphere. So cancels, 2 left over, bring them up. So that becomes ATM to the minus 2. Nice. Like that. That was fun. Moving on. The pressure on the system is doubled at constant temperature. Explain the effect of this on the yield of ammonia by considering the change in Kp and hence the position of equilibrium. Okay, so they doubled the pressure. Well, the yield will increase. Yeah, 4 moles on the left, 2 moles on the right. So the yield's going to go up. So first thing, the yield of ammonia will increase. However, Kp will remain the same. Kc, guys, it's all a trap. Kc and Kp are only affected by temperature. That is it. Otherwise, it will be returned to normal. So it remains, Kp will remain unchanged. Right, now we need to talk about the partial pressures to explain this. So what's going to happen is, well, imagine the equation. So all of a sudden, I suddenly up the pressure. Yeah. And what you realize is if I just like, let's double everything. 180, 80 becomes 160, 25 becomes 50, and this becomes 300. Right, let's translate this over to here. 160 squared equals, that becomes 25,600. Yeah, look what happens to the bottom number. 50 multiplied by brackets 300 cubed. Oh my goodness. That bottom number becomes 1, 3, 5, 0, 1, 2, 3, 1, 2, 3. So it's massive. 25,600 divided by 1. Oh, divided by answer. Right. And all of a sudden you realize that the KP has dropped. Yeah. The reason being is the denominators are going to increase greater than the numerators because there's more of them. So the partial pressures, I'm just going to write PP, partial pressure of species, partial pressures of denominators, partial pressure of the denominators increases more than numerators. I don't like all that. Partial pressure of the reactants. It's better. Partial pressure of the reactants increases more than partial pressure of products. Now, here's the thing. I've just calculated a brand new KC. Sorry, brand new KP. I'll do it in green. New KP. New KP is 1.89. It's actually 90. 1.90 times 10 to the minus 5. It's actually got smaller. Now, this makes sense. Now, here's the thing, though. So why have I just stated that it doesn't change? Because now the equilibrium is going to shift. And the gases are going to be now, the partial pressures of the reactants is now going to drop as the equilibrium adjusts for the increase in pressure. And as it adjusts, the ratio of the two will be returned to normal. So KP of reactants increases more than the products, but equilibrium shifts to reduce pressure, and case and KP will return to previous value, unchanging. Right, guys, that brings me to the end of the paper. Let's mark it. Yeah, that's been fun. That was a lot easier paper than the January. Like, it really was. Like, the other paper was a lot more extensive. Like, went on the graph, absolutely sucked the time out of me. It's a nightmare, that graph. No rate graph. It's lovely. Right, let's mark this. Let's mark it. Remember, never, ever, ever walk away from a paper after doing it without marking it. Okay, let's see if I get any of my multiple choice wrong. C. It's good. B. A, D, and D. Doing well so far. I still think I'm going to usually get at least one wrong. B, I got one on the AS paper wrong. A and B. Doing really well on the multiple choice. D, followed by C, followed by 9C. A, I've got it wrong. Wow. There you go. That bloody indicator. It's not within the vertical region. Oh, that's a bit. Yes, that was harder. Right. Well, I still got my indicators wrong, and all I had to do was compare values. Like, how ridiculous is this? Yeah. So revise using the indicator list. I'm an idiot. I do want to go back and check, but I can't be bothered. A, I'm happy. Can't believe that. Of all the questions to get wrong, B, that's hilarious. C, oh, it's really made me giggle. B, C, and B, and the last one was D. Doing well now. On a roll. Section B. Oh, the nightmare that is section B. Top line, bottom line, either. I'm going to take those as all red. That I've made sure that they're all correct. Yeah. It's fine. Next, am I going to get the right value? Right, you get 1 mark for this crazy equation, and then the final answer is what? Oh no, have I made a mistake somewhere? It looks like I may have. Where's the final answer? Oh no, what have I done? What have I done? What have I done? Oh dear. 2 times, yeah. 2 times 3, 4, 8, yeah. There's my final answer. I'm out. I've stuffed it up. Stuffed up my calc. Right, I'm going to run that through again, and I'm going to check, because I've made a mistake, guys. I've made a calculator error. I've got the right equation by the looks. Oh, yeah. Okay, let's just type that through again. So, guys, I would definitely get most of the marks for my working out, but my answer is wrong. Let's run that calculation through again and see if I get the same answer. Minus brackets plus 590, close brackets. Yeah. Minus brackets plus 178.2, close brackets. Plus brackets minus 795.8. Yeah, 795.8. Yeah, close brackets. Minus brackets minus 2258. Yeah, close brackets. Minus brackets 2 times minus 3. I bet that's what I missed. I bet that sign there is what I missed. Plus brackets 2 times plus 121.7. And I get the same number that I did before. What have I done? Oh, what? What is going on here? What's the final answer? What is my final answer? It says I've still got it wrong. What? They're saying it's 1150. What have I gone and done? Have I included something I shouldn't have? But the equation that they've given me there is exactly the same as the one I've just done. What have I done? Well, I just typed in exactly what they just did at the top, and it didn't work. This is really horrible. This is irritating me. This is really bugging me. How have I managed to get the numbers wrong? How is theirs right? I want to look at that number. I'm going to run that into my calculator and see if I get the answer they want. Minus 590, minus 178.2, minus brackets, 2 times 121.7, close brackets, yeah, plus minus 795.8, minus 2258, minus brackets, 2 times minus 348.8. And I now get their answer. Okay, 1150. Where am I different? That's my question. Where am I different? Minus and a plus is a plus, right? Have I gone and there's my error? The very first one. Have I made a mistake? Plus 590. And is it going in the, oh no. It's going, oh no, first one. First ionization energy goes against me. Oh, if I read it wrong. Where's the standard enthalpy of formation? It's with me. Oh no. Oh, I've got all kinds of, I've done something very odd here, guys. Number one is I've changed that sign there. I've made an error there, folks. So there's my error. I read it as a plus and it should have been a minus. So there's 1. Yeah, look, there we go. No, wait a sec. No, I haven't. That's correct. What am I doing? That is correct. Oh, hang on a minute. Oh dear. Right, start from there. First one is the first, that one there is the first ionization of calcium, and it is against me. First ionization is correct. That point there is right. But they're saying it's not. They're saying it's negative. Why? It's going against me. I'm starting there, and it's going up. Why are they saying it's negative? That's the difference. I'm going in the other direction. We're trying to find the second ionization energy. Winkit, help. We are going upwards, which is always plus. Should it not be plus 590? I've made a mistake here somewhere, and it's hard to identify what I've done. Bourne Harbour is one of my best things as well. I don't like it. What have I done? I never make a mistake on these. The first ionization energy goes up, but we're moving in the other direction. So it's against me. So it's minus a plus, which is a minus. Yes, which is what they're saying. Minus a plus, which is a minus. That's okay. That one's good. Right, next one, which is this step here, which is the atomization of calcium. Atomization of calcium. That is a plus. We're good, which is what they've got. Yes, so far we are identical. Next, right, this is where we then differ because they went into all the 2s. The next thing is to show that that is the same as me as well. Yeah, but they're saying it's minus. And I've said plus. I've gone in the wrong direction. I've said it's with us, and it's not. That's 2 times 1, 2, 1. Atomization energy of chlorine. Oh, no, that's okay. Yeah, no, atomization. Oh, nuts. I've done it out of what Okay, so I realized I've gone wonky. So should we get, no, it's okay, Winkit. I've just made an error here. I can fix this, look. So the equation that I built, let's just move it back over. Oh, sorry about this, folks. And it is worthwhile taking the time for me to analyze where I went wrong. Like, I'm so solid usually with Bourne Harbours. They're one of my best functions. And so it's worthwhile chatting about it. Change my color. My equation starts here. Right. We're heading in this direction. This one here is against me. And that there is the first ionization energy, which is that. All good. Next step is the atomization of calcium. Atomization of calcium plus 178.2, and it's going against us. That's correct too. Next one. This one is with me. This is the enthalpy of formation. So the enthalpy of formation, this was number, I want to cross them off as I do it. First ionization energy, done. Yeah, atomization of calcium, done. Yeah, next one is the enthalpy of formation. So the standard enthalpy of formation, which is that, and it's going with me. That there is correct. Next, this one is going against me. The sign's good, and the value is minus, that's the enthalpy of lattice. That is also good. This one is going against me, which is minus 2 times the electron affinity. Electron affinity of chlorine, yeah, that's okay. And then the final one is with me. With me? No, it's not. It's against me. It's going up. There's my problem. There it is. Minus 2,120. Found it. So easily done. Ugh, and you'd lose all of it. You'd lose boatloads. You'd lose 3. No, I got no units. It's just really easy. So if I now take my value of 1635 and I go, oh no, okay, let's just run it through. Minus brackets plus 590, close brackets, minus brackets plus 178.2, close brackets, plus brackets minus 795.8, close brackets, minus brackets minus 2258, close brackets, minus brackets 2 times minus 348.8, close brackets, minus brackets 2 times positive 121.7. And I get the exact same answer, 1150. So close with positive, so close. So easily done, folks. So easily done. So easily done. Oh well, let's keep going. Made a garbage mess of that. Let's see if I get the rest. Okay, 1, 2, 3 more. So explain why it's different. So bonding is partially covalent. Ca2 plus is highly charged or high charge density, leading to polarization. I like it. Done. Next. Explanation of the following. On lattice, enthalpy becomes less exothermic. So energy is released on formation. Attractions are weaker since less energy. I've made another mistake. Less energy. I was meant to say less. Yeah, that's the mark. I'll lose that one because I didn't say the word less. I just skipped it in my writing. As the radius of metal ion increases, the ions increase in size. Lattice enthalpy becomes less exothermic. Size of ion allow less attraction to the weaker bonds. Do not allow just weaker bonds. Penalize specifically molecules. Discuss polarization power. 3 marks. 1 mark for saying lattice enthalpy becomes less exothermic. That's a bloody question. Radius of the ions. So I've definitely got that one. The third one. The weaker forces of attractions between ions. So the amount of covalent ion. So the anions are less distorted, so less energy is released on the formation of, since attractions are weaker. I'll definitely give myself 2. Definitely. Forget this one. I'll kick myself. There we go. That one's okay. The equation is solid. Next, pentanoic acid. All 3 branches. Bunched. That's good. Interested about these values. Allow a value range within the range. That's funny. 1.5 to 2.9. I said 1.6. Yeah, that's okay. It's within the within the range. 3 marks. Yeah, it's within the range. Triple singlet. 5. Okay, I hated this question. Identified F. So F is that guy. V is ethanoic acid. And W is propanol. And any 2 of the justification points are allowed. Infrared spec. Smell master. Yeah. Dumbo. Dry ether. Lithium tetrahydride in dry ether. Yeah. Catalyst. Nice. Ignore any mention of homogeneous. Fine. So A has the highest boiling point. Molecules held together by hydrogen bonding. Hydrogen bonding are stronger than other intermolecular forces. Nice. Concentration equals 7.0.075. Yeah, and then the next one is 1.33 times 10 to the minus 13. Oh, I didn't use my units there. Should have put units, but still. Next one, 34.3. Like it, 4 marks too. Boom. Conjugate acid base pairs. Yep. Oh, this one was horrible. Oxonium ion produced in first association pushes second equilibrium to the left. I get both for that. Yeah. But allow doesn't need any of those. Fine. Correct expression for Ka. Oh. Allow H plus. Do I need state symbols? Do they want the state symbols? No, they don't. They don't need them. Do not award the charge outside the square brackets. Yeah, that's okay. Understand that one. Next. So 7.96 times 10 to the minus 3 is correct. Assumption. Routing everything. Moles per time cubed units. Large reservoir. Adding OH minus H plus adding OH combines with H plus to form water. Dihydrogen phosphates dissociate. Add reacts with equation perfect. Ratios and the concentrations ratios hardly changed. Next one, entropy of the system 198.198.8. Yes. Given expression. Yes, expected sign. 4 moles, number of moles decreases. 157.4 joules per chem per mole. Thank you very much. So that's then going to walk us into this one at plus 236. Yep. 0.1, fine. Joules per chem per mole. Next one, this was this disgusting thing, which is just grimness. Just grim. Rate of reaction is higher. Ammonia production in a given, more ammonia produced in a given time. Ooh, never mentioned that one. Higher temperature, less positive since temp higher. Delta S1 is less positive. Therefore, delta S total is more negative, less positive. Kp decreases, equilibrium moves. That makes the reaction less Kp. I mentioned Kp. All right, the equilibrium constant will be reduced. Yeah, shifting it to the left. Less feasible. More ammonia production in a given time. That's the only thing that I've missed. And that was the whole uncompromised temperature used to balance rate and yield. Allow reaches faster, higher alternative rate, higher cost without justification. Yeah, okay, Winkit, I'll give you it. That whole thing of ammonia, more ammonia produced in a given time. I feel like that's a bit of a mean one, that. I've definitely got all but that mark. Yeah. Anyway, those waffly ones, I don't mind losing stuff on. Kp expression, allow capital P, allow 1p. Fine. 7.9, calculate the value of Kp, 7.59. Ignore significant fig except for 1 sig fig. Yeah, I'll take it. 10 to the minus 5. Yep. ATM2. Nice. Yield of ammonia. Kp remains the same. With the equilibrium shifts, and Kp will return to previous value. Kp remains unchanged. Quotients. For the equilibrium shifts. Kp expression. Yield of ammonia will increase. So equilibrium shifts right hand side. Kp remains unchanged. Fraction quotients decrease in the value. increases more than products do. So equilibrium shift to right-hand side to return it. I'll take it. Yeah. Okay, I'm saying the right things. And that brings me to the end of it. God, how long's that taken me? 2 hours. I'm done. Oh. Yeah, I lost that mark as well. I think on an old spec paper. Yeah. Stop share. Yeah, it's one of those things, Winkit, marks like that. So they're just wanting you to waffle some. So the takeaway there for me is when they're talking about equilibriums and they're talking about in that entropy setting again, we'd be saying things like, so it does this to the surroundings, it does this to the total, therefore the yield, therefore but the rate increases, and they choose a compromise because it have a good rest, Mr. Duncan. Thank you very much for doing this. Yeah, it's just they realize that they want to say that industries choose this because it will maximize their profits because they will make more ammonia in a given amount of time. It's the compromise. So it's just a reference to the actual output, which is just stupid. It doesn't need that. Anyway, Winkit, thank you very much for coming along. I hope you find it useful, and I'll probably see you tomorrow for Unit 5. I'll see you later.